I need consensus from everyone of you. Yeah, but is it possible that you guys manage without postponing? Because I changed today's lecture because there is an exam on Friday. So the whole thing will get disturbed again. Like earlier, because it was last week, I changed it again. So it will really get delayed by a week. Let's see how important it is for everyone else. Okay. Okay, it's up to you. If you can convince everyone, that's fine.
Even you or
Then comes me. If everyone gets convinced, then I will be less. I have to obey them. Let's be democratic. Okay, let's go by the number of people. Yeah, with my vote also one. Okay, reasonable. So we have 6 students and 1 for 7. So you need 4 votes. Yeah. Hello, Niranjan. Yeah.
Good morning, Dr. Sadesh.
Oh, so homework 9 surely is on. No, not October 31st, November 6th. Midterm 2, as far as I know, is November 6th. Right. And let's put a deadline. It cannot be changed after tomorrow. Okay, so whatever you guys decide, let me know, and in a common email to all of us, right? And unless I write an email with that it has been postponed to all of you, it's not postponed. Okay, so there should be no confusion because it's a last class. There is no confusion. By default, we are having the exam on Friday, unless you will see a serious email from me that it has been postponed. Reasonable?
Number 6 is
Not a Friday?
Monday.
Oh. Add it to the confusion. The argument is going to win. Okay. 30th, 31st, yeah, November 3. Thank you. Thank you very much. Yeah, okay, that would have really confused. Okay. Again, exam will be on Friday unless you get an email from me, let's say at the most by Wednesday morning. Okay, after Wednesday morning, even if I write, it's not cancelled. Okay, otherwise some weather or something serious has to happen. Okay, that has to over. Okay. Anything you guys want to say about the content for midterm 2 or anything in general?
Today's lecture will be included.
Yes, everything that we cover until the exam. For example, if it is postponed to Monday, then even the Friday comes in. Right. So usually that's what I do. But having said that, probably a good amount of complex analysis. That's what it will be. And even the ones before, but probably very less. The expectation is that I concentrate on something.
have you decided if it's in class or a common class?
In class, probably a good bit in class, and then outside also. That was primarily because of I think complex analysis. I was not satisfied with the homework, so we will have it. And how much I divide the take home part, that will be decided at the end. So what I mean by that is that you come to the class and see that out of the questions, 2 are supposed to be attempted here, and then you take home and then bring it back the rest. So 3 questions could be take home. That way I make the assessment less assessment is easier on your end. On my end, if there's only 2 questions, really seriously contribute, because the rest of them you have, and you can use the internet whenever it's straight home. The internet, and even you can discuss with others. Yeah, I'll talk about those things. Anything else? Yeah. Okay, we talked about harmonic oscillator, and in particular damped harmonic oscillator. So we're talking about damped harmonic oscillator. And what is missing in this is that I can make this forced. So currently it is not forced. Okay. So I'll talk about that in a minute. So what we have is a spring that is stretched. That's your x, and that is 0. So if it was at equilibrium, it will be at position 0, and it gets, if you stretch it, it gets pulled by kx minus kx. In fact, if x is positive, forces towards a negative direction. There is also friction, and the friction need not be on the surface. Let us not think of it as a surface. Instead, let's say it is friction due to air. The idea being that whenever you have a fluid, it is velocity dependent friction. When it is a surface, it depends on the normal force. So it's not the surface of contact that is providing you the friction. It is the drag forces that's providing it. Let's also put an external force, F of T. That's what we mean by forcing. The forced harmonic oscillator means someone is oscillating it. Correct. Someone is actually pushing it up and down. The Newton's equation in the x direction would be minus kx minus, let's say, this is a position dependent force, so that's your spring, which is position dependent. That's your drag, if you want, not really the friction. This is velocity dependent. That's one thing you should realize whenever we were doing 200 level physics. That means the first physics that you took at calculus, university calculus based. Most of the forces you do there is mostly constant forces, right? Normal force, tension force, they are constant. And spring is the first force you see that is position dependent. Drag is the first force you see that is velocity dependent. And when it comes to gravity, there is a 1 over inverse square law, which makes it really elaborate. And here we also say that force is towards the right, so it's plus F, which is a function of time. That's the force with which you're oscillating. But we are not putting the forced harmonic oscillator, so we are going to put that 0 in a minute. But let me write this as m second derivative of x position with respect to time plus d times velocity dx by dt plus k times x. That's equal to f of t. In this way of writing, notice that x is the unknown here. X is what I would like to solve. So this is a homogeneous or inhomogeneous differential equation at f of t is 0. So this is an inhomogeneous differential equation. And if I set, so let f of t be equal to 0, then we have n times equal to 0, that's homogeneous. And I want to stress the difference in the sense that when we say Green's function, we want to talk in terms of Green's function. What Green's function does is that if you know the solution of a homogeneous differential equation, Green's function is a technique which lets you solve an inhomogeneous differential equation. So if you know the solutions of a homogeneous differential equation, which often is easy, if you know it, then for any given source, notice any given source, Green's function gives you is a technique to solve an inhomogeneous differential equation. So for now, today, we will keep this homogeneous differential equation. We will solve it. We'll just talk in terms of extreme situations when this is dominant, when this is dominant, or the third one is dominant. And once we have those solutions, next time we will come and try to introduce the source, and we will talk about the Green's function technique. That's what the idea is. Any questions in that? Okay, so the Green's function allows you to solve for this equation. We are going to currently solve for homogeneous differential equation, which we mostly did last time, but then we want to see some extreme situation limits and see how it works. There seems to be 3 parameters. Yes, there are 3 terms, right? And often you want to think of what if this was dominant. Out of all 3, usually one is weak. You can think of it as one being weak, or 2 of them being dominant, or one of them being so dominant that is only one term in the equation. This is an inertia term, so you call this inertia. And that's mass times acceleration, right? That's the inertia term. This is the friction or drag, let's say. In this scenario, that's the drag. And that's the oscillatory contribution. Again, the idea is that in this case, since inertia is always needed, if oscillatory term is more dominant than the drag term, then it will oscillate. If the drag term is more powerful than the oscillatory term, that will decay. If this was not there, this will simply decay, right? Remember drag forces like the terminal velocity problem. If you were to jump out of an aeroplane and you wait for your velocity, it will saturate. So there is an exponential decay of the velocity, and that's the terminal velocity, and we will talk about that. Out of all this, the way we are going to do today is that this will always be there. The inertia term is not going to be neglected, right? So this compared with this compared with it, but this will always stay. It is almost like saying, can you think of Newton's equation? Newton's law says that mass times acceleration, inertia term, is equal to the forces. Is it possible of thinking of a scenario where this term is not relevant? The inertia is not relevant. Can you think of a situation where inertia is not important?
It's like attraction between some 2 atoms.
There is electrostatic force, But inertia matters, right? For example, if the proton is very heavy, then it will behave in a certain way. If the proton was lighter, then it will behave in a different way.
For photon, right?
Tell again?
For photon, there's no mass.
Photon. Let's not do that because Newton's law pretty much fails for photon, right? Then mass times acceleration mass is 0. So then we have to come up with a different equation altogether. Yeah, I was still thinking of non-relativistic physics. Good point there, but I think there, if I'm not wrong, inertia is more important for some. Even though it doesn't have mass, I think still the kinetic energy term will be relevant. But I could be wrong. I mean, the moment you're asking, I'm just thinking of in my head. Yeah, let's not go into photons. Like in realistic, normal day-to-day life, what will happen if the mass times acceleration term was not relevant? Like when does that situation happen? That in Newton's law, the mass times acceleration, which is kind of the fundamental statement itself, that's not there. And this is conceptually hard and mathematically also harder to incorporate because this is a leading term in a sense in the differential equation that goes away. But this is, I shouldn't say mathematically very hard. It has been analyzed very well and it has interesting effects. And in your homework, there is an article I asked you to read. Like I don't really ask you to do the calculation, I ask you to read. And that problem discusses this fact that what if the inertia term itself is negligible, that it is not important. And if you think of bacteria moving in water, let's say, and apparently in that case, this term is not relevant. And the main point is that then the good analogy they make is that if you were to swim, we always have an intuition for swimming, right? We actually push and then you go forward. But if this term was not there, that's not that simple fact, that simple intuition doesn't work. And bacteria have their own ways of non-trivial ways of movement, which comes primarily because this term is not relevant. It is, you basically say that it is, the inertia is, or the way to say it is that the time that it takes to react. So for example, someone hits me, I have to react to that. For example, sunlight comes, it takes 8 minutes for me to realize that light from the sun has to reach me. And then I have to react. And it takes some time for me to react. And if that time is small or big compared to the 8 seconds it takes for the sun's light to reach me, accordingly, it matters whether my inertia is important or not. So if it is not important, for example, before I could react to whatever is happening to me, if that is already gone, if the reaction time is significantly small, then the inertia is not there. Plasma is another example. Plasma is electrons and protons, and when they move as a gas, then again you say that inertia is not important in that case, even though both protons and electrons have mass in it. But in the plasma oscillations, you say inertia term is not. I'm not motivated in the strict sense of neglecting this in terms of that. So I will not do that because I think conceptually very quickly gets harder to incorporate, at least from my perspective. Okay. So we will talk only about situations where drag is negligible or oscillations are negligible. I won't talk much about when inertia is negligible. When inertia is negligible, that's your last problem in your homework. I motivate it in the context of the paper, and I highly recommend you to read that. At least read it superficially. At least read one page of it. Like after a while, it gets harder to understand. But the first page should be sufficiently motivational that you should understand what the problem is talking about. Basically, neglecting this term in this equation. So coming back in here, so if there are three parameters, usually if it is 0, we can divide out, but if it is not, for now, let us one more step, let me write this and I set f equal to 0. So divide out by mass, so I have second derivative e squared, and b over m, let's say is 2 times gamma. It is plus 2 times gamma d by dt, and k over m, let's say is omega naught squared. That's the oscillations if there was no friction. So that's plus omega naught squared, and the whole thing of t, and this will be equal f of t over m. Let me define that also, f of t over mass. Let me call that a of t. This shouldn't be confused with amplitude. I call it a because force over m is acceleration. I don't want to call it the small a because the acceleration itself is the first term here. So some forcing has an acceleration associated with that. So that's your a of t. But then we will come and say that I want to introduce a negative sign on both sides just for conventional reasons. That's how I have been doing this for consistency. I'll put in a negative sign. But it should not affect today's class because today I'm going to set this to be 0. This is 0 for no forcing. But we'll come back and introduce force. So that's your equations. That's last time. Let me very quickly remind you what we did last time. Last time we said there was no friction. Most of the time last time we did no friction. That's equal to 0. That's basically harmonic oscillator. And plus there has to be boundary conditions, right? So you said x of 0 is equal to x naught, and our velocity at time t equal to 0, we said was v naught. So I can at time t equal to 0, I can have x naught and v naught, and the solution was x of t is equal to what was it? That equal to 0. So it has to be x naught times cosine omega t. And sine becomes a cosine, so it's e omega t, so it's v naught over omega naught. Notice differential equation always requires the differential equation itself plus the boundary conditions, right? Otherwise, it's not a well-defined equation. This time, so here, notice if you go back, oscillation was important. If this was dominant, that's what will happen, correct? If this was dominant, I can neglect this. And then I have to add this as a perturbation or a contribution to this. But let's say if this was neglected, and if we only have the drag, so let's come to that. So that was one part we did. And second piece is you have x over e squared plus 2 gamma x by dt is equal to 0. What's the solution to that? Is that a familiar? It may not look familiar because I've written it slightly. So let's write this on the right side. Dx by dt is v. So then I have dv by dt here. Right. and that's equal to minus of 2 times gamma times this is v itself. I think my gamma and v all look the same. So that's gamma and that's your velocity. Okay. What's the solution to that equation? Very good, exponential of minus gamma t, right? So plus, now notice I need only one boundary condition here because this is pretty much a linear first order differential equation. I need only one boundary condition, but let's at some level it is second order. So let's say x of 0 still is x naught, and velocity at time t0 is equal to v. In general, I can have any solution. And as one of you said, this has an immediate solution. Integrate both sides or separation by parts. Let me do that in 2 steps. So velocity v over v, that's minus 2 times gamma times vt. So that's separation of variables. If you want, integrate on both sides. Right. So that is log of v is equal to minus 2 gamma t plus a constant. That's an integration constant. So velocity as a function of time is equal to exponential of minus 2 gamma t and exponential of c if you want. Put in your boundary condition that velocity is equal to v naught at time t equal to 0. So boundary condition v0 is equal to v naught implies that, so this is v naught is equal to v raised to c. That implies that velocity v as a function of time is equal to v naught times exponential t. Now, is that correct? Okay. Yeah, this is not. Yeah, what is the difference between this and the person diving out of the aeroplane? Like usually you have a terminal velocity. Like, is that clear what I'm saying?
Should be plus. So
Plus?
the exponential should be plus for the diving.
No. Or what I, so maybe the question is not clear. So if I were to plot this as so this velocity is here time t, this is the curve here, right? So this is v naught. Right? Velocity starts with a maximum and then goes down to 0. But we know that terminal velocity increases, right? You start from 0 typically. So in a, can you move the camera? Yeah, so if you have a, so this is a person jumping out of an aeroplane. How does it look like? So that is a terminal velocity vt. That's your curve. So what is the difference between the two? What changed? Why is it different?
Yeah.
Damping here, that is in the terminal velocity, wind is the damp, right? The drag forces, this is damp means that there is a drag force which is velocity dependent.
But they're opposite direction.
They're opposite direction too.
It's mg and
There is mg, but there is no mg here, right? So this equation would be, so if I were to write mass times acceleration would be equal to minus v times velocity, then there is plus mg there. So there is a gravity that is accelerating it, and drag force is resisting it. So somewhere in between they balance out. So this force is not there, this constant force is not there in our analysis. So since that is not there, this is for this is terminal velocity. In our case, this is not there. Like that's the simplest thing that you can do. When I put in a inhomogeneous differential equation, that's a constant term I can put in, right? So I can put something on the right side, and that could be the force. But here we are talking about this scenario, right? So this is a diagram completely just to realize that that is not the equation. Now, if so now we have two solutions, correct? One is if there is a drag that is dominating versus an oscillation that is dominating. Maybe I should do a little more because now we have velocity. We should integrate this to get position, right? So let's get the position also. So dx by dt is equal to v naught times exponential q gamma t. So x as a function of time is equal to integrate this. So it will be minus v naught over q gamma times exponential of q gamma t plus a constant. Again, a different constant from here, but that's what it is. So again, put in the boundary conditions. You have x of 0, that's not is equal to minus not over q gamma plus c. So c is equal. This implies that c stop plus not. That's the same as, so your solution would be x t equal to how about that right? 2 seconds. That's just a way of writing it, doesn't matter how we. All right, so that's your set. So this is the solution for drag dominant or damping dominant, but drag dominant or either you say damping dominated or drag dominated, and here is the case when oscillation dominates. And anything in between has to stay between the two, but now let me have the two plots in the same graph. So that's your time. That's my position, x. X is a function of time. Depending on what my x naught and velocity is, I can start from 0 or from a maximum. It depends on the initial condition. But whatever is my initial condition, here it will oscillate, right? Xt will oscillate. That's my oscillations. So this is a scale which is omega naught over 2 pi over omega naught. The time period is 2 pi over omega naught. Let's say t is equal to 2 pi over. And there is another constant, which is the exponential. Again, it depends on, I can go up and then come down. I can come down straightforwardly. That depends on my initial conditions. But whatever it is, after I leave my origin, there is a scale, and this is decided by exponential of -2 gamma t. Right? At the far end, that looks like that. But this has to change between these two for large time period. So what is happening is that if omega naught is large compared to your omega naught, what exactly is happening? So yes, Fish.
Why does it look like a cost function? I mean, the graph.
Are you asking why is it not starting with the sign?
Yeah.
It depends on my initial conditions.
Ah,
Right, so if, let me put it, so that's why I did not go there. Right, so maybe, the question is if. If x naught is equal to 0. And the v naught, v as a, and v naught is not equal to 0. What if both are 0? Huh?
you know.
If both are 0?
No, start.
It is 0, you mean to say? What, so basically it doesn't, nothing happens, right? If you don't, I mean, it is like saying if you don't stretch it and if you don't give a push, nothing is going to happen. Only in homogeneous differential equation. In homogeneous differential equation, this is a trivial boundary condition. Nothing happens. But if it is a forced harmonic oscillator, then it can happen because even if you start from rest, because someone is pushing it, it can induce a motion. And the moment you push it, then there is motion. So in that sense, currently we are doing homogeneous, so that's not the case. So let's say this is not equal to 0. If that is the case, then my solution would be P x naught. This is my x naught. So I need to have a no displacement at x equal to 0, so it has to start from here. So this will be, so if this was harmonic oscillator, it would have gone like this. And if it was decaying, if it was pure decay, then x equal to x naught is let's see. This is 0, but I still can have velocity in here, right? So since velocity is there, how will it look like? So that's your x. This is no drag. Right. If x naught is equal to 0, v naught is not equal to 0, and pure, well, let's say no oscillations. And in that case, again, I have to draw this. So notice now it is a position, x naught is 0, v survives. How does this graph look like? So I have to exponential decay looks like this. So this exponential decay looks like this. I have to reverse the sign of this minus, and then add a 1 to that. So this will look like this. Right? But this is position, notice. It's not. So this is V naught over 2 times gamma. What we are saying here is that I start from 0, but I give it a push. Right? I start from 0 and give it a push. That is, initial velocity is not 0. And then ask where will it come and stop? Like it will eventually come and stop there because there is a damping force in there. And this is where it will come and stop. It will go this far and come to a stop. I have a mass m. I push it to the right with an initial velocity v naught, and then do not give any force. This will slowly come to a stop. There is no spring. Is it clear? No. Again, no spring. Okay, so this is so that is no spring, so kx is equal to 0. No spring. B times V is not equal to 0, so that means there is a drag is there. The tick mark means the drag is switched on, and there is an initial velocity V naught. So there is an initial velocity V naught. I push it, it tries to slow down and eventually come to a stop. But while it has come to a stop, it will go a certain distance. Right? It starts from 0. How far will it go? That's the question you can ask. And it will go a distance of V naught over 2 times gamma. How long does it take to reach there? How much time does it take to reach there? How much time does it take to reach there? That's time. That's position.
Work together.
This is time. That's position. I'm asking how much time does it take to reach this one? Or when does this intersect that horizontal line? Never, right? So it will never come to a stop. Technically, theoretically speaking, it will never come to a stop. It is trying to come to a stop. It's like the terminal velocity. How much time does a skydiver take to reach terminal velocity? If it is exactly the same curve here, it never really reaches. But if you say within 2 significant digits, how much time does it take? Then it makes sense, because then it is 99%. But unless you give a percentage of the terminal velocity, it will never reach. Like it never intersects in a sense. So, but still there is a time scale in the sense that is gamma, right? So somewhere here is your gamma for 1 over 3 gamma, which is called the time constant. And that means that what happens at 2 times gamma, maybe that's also an important piece that you comment. At 2 times, maybe I'll do this. Okay, yeah, so x of t. Is this really readable, Niranjan? I'll go that side. Yeah, maybe now.
That helps, yeah.
Yeah, okay. So x of t for the initial conditions, I'm saying x naught is equal to 0, v naught is not equal to 0. That's equal to v naught over 2 times gamma times 1 minus 2 gamma times t, right? This has a curve which is like that. And that is v naught over 2 times gamma, that's your x, that's your t. And then you ask, there is a time constant here. How? That's equal to 1 over 2 times gamma. So what happens at, so how do you define your time constant? Time constant is when t, what you're asking, what happens at tau equal to, that's correct. So let's say x of t or x of tau, right? X of tau equal to v naught over 2 times gamma times 1 minus exponential of, this is at tau, it is 2 times gamma, so this is minus 1. When I put t equal to tau, that is 1 over 2 gamma, that cancels out, so I have exponential of minus 1, and this is nothing but 1 minus 1 over e. What is e? E is the exponential, it is 2.7. right? At least your two sig digits, it's 2.7. And 2.7 minus 1, so that's 1.7 divided by 2.7. This somehow will be about 0.63 from the two significant digits. That's 0.63. 63. That means we say that time constant is the time when the position of the object in this case is 63% of the total. Like the total distance it would have traveled, if you let it go all the way to infinity, is P naught over 2 gamma. So how long does it take for it to go 63% of the total is what time constant is. In the case of terminal velocity, since we cannot ask how much time does it take to reach terminal velocity, you say how much time does it take to reach 63% of the terminal velocity. That's called the time constant. In decay problems like radioactivity, it's the same problem. If you ask how long does it take for it to die, it is infinity in the sense that there will always be something or be something left. But instead you ask how much does it take for it to 63% die, or sometimes if this constant is not there, then it is the remaining 0.33% or 37%. But so it is a percentage. Sometimes we can also say 99%. There is nothing special about this type constant. You can say 5 times the time constant and so on. Okay, so that's your extreme ends, but we want something when both are there, right? And when both are there, you should be able to take the limit when the drag term is dominant, and you should be able to get this solution out of it. And when the oscillation terms are prominent, you should get this. And then when the drag term is dominant, you should get the other. Those two dominant terms we should be able to pick. So what is the general solution? And this is what you do in your homework. You start from the general solution, and you should be able to get these two limits in by doing different limits. So reasonably straightforward, but still that's your homework. That's not other much. So again, going back to our equations, our second derivative d squared plus 2 times gamma times d by dt plus omega naught squared times x of t is equal to 0. That's our equation. We can put in a negative sign, but when it is 0 on the right hand side, it doesn't really matter. We want to look for a solution since it is a linear second order differential equation. Linear in the sense these are all constants. The coefficients are all constants. The expectation is that just an exponential of alpha t might be a solution. Just any alpha t, and alpha could be complex. Alpha could be complex. And immediately you put in second, each derivative brings in an alpha, right? Derivative of exponential brings in an alpha, and we learned that this is alpha squared plus 2 times gamma times alpha plus omega naught squared times x of t. Exponential is returned back when you take the derivative. That's equal to 0. We roughly did this last time. You're looking for alpha if there are two possibilities, either the x is 0 or the quantity in the parenthesis is 0. If x was 0, that's a trivial solution, then there is no oscillation at all. So that's not of interest. So we want this solution. So alpha must be equal to gamma. It's 2 times gamma, then you divide it out by 2. So I'm doing that ahead of it. So this is gamma squared minus omega naught squared. that was the idea of putting this factor of 2 and this, otherwise this will be 2 gamma squared divided by 2 in that. Let's, it depends on which one is dominant and how you approach the problem. Let us write this as gamma plus or minus, let's say omega naught was dominant, so this will be I times 2. So maybe what I'm trying to say is that if gamma was larger than omega naught, if gamma was very much larger than omega naught, that means in the extreme limit, I don't even keep omega naught. Then I have two solutions here. One is 0. So alpha is either it is 0 or it is 2 times gamma. In the other limit, if I were to say that omega, so gamma is very much small compared to omega naught, that means the oscillatory terms are dominant over the damping terms or the drag terms, then I keep only omega naught, right? First, the gamma is neglected. There is an omega naught in the square root, but then when I add this to gamma, this is also small so that I can neglect. And if gamma is small, I can neglect at least. So this will be plus or minus I omega naught. The extreme scenario where really nothing else contributes, right? But we would like to keep the small terms. And this you immediately see. So then the solutions here are, so solutions in this case will be, if it is 0, it is 1. Right, so this is 1 and exponential of 2 times gamma. Why does 2 times gamma? Shouldn't it be minus? Up. When it is plus, well, it is plus. We got minus, right? Was that wrong? No, doesn't grow, right? Okay. Plus,
The first gamma should be negative.
first gamma should be negative. That's correct. Minus b, right? Thank you. Thank you. Yeah, that's the okay. First one should be negative. Yeah, that's how it's yeah. So yeah, that's very good. So then it's plus 0 and minus 2 gamma. Yeah, thank you. Yeah, okay. That matches with what we have. So our intuition is matching with that. Otherwise, something would have been wrong. Otherwise, it's going to grow. Yeah, thank you. So, okay, and in this case, our two solutions will be e raised to I omega naught t and e raised to minus I omega naught t. And we have also said that we don't have to be always working with exponential. We can work with sine and cosines. And whenever it comes to oscillatory terms, at least in this case, nothing special about sine and cosine. We have been trying to work with sine and cosine when it is oscillatory and exponentials when it is damping coefficient. So put this extremes apart, come back to your total solutions. Your solution would be exponential of gamma, so it is minus gamma t, and this will be plus omega naught squared minus gamma squared, and there is an I. The I means there will be an oscillatory solution to that, and there is a time t. This e, or exponential of minus gamma t minus gamma t and exponential of minus I. have to write the exponential. That's operation. As I said, when we are doing oscillations, I can put sine and cosine of it, or we will like to use cosine of omega naught squared minus gamma squared times t, or sine of either the top or the bottom or any combination out of that is perfectly good solution. We will say the second line is what we go for. So let's say this is a time a and b, some arbitrary constants. This is gamma times t times cosine omega naught squared times gamma squared t plus b. Often you give it a new letter for this frequency, so that's omega squared. Notice the frequency has decreased. Right, the frequency has decreased, so omega is equal to square root of omega naught squared times gamma squared is less than or equal to omega naught. If the frequency decreases, the time period, the time period which is equal to 2 pi over omega naught is greater than or equal to t naught is 2 pi over t naught. So if there was no damping, the first oscillation, right? So if there was, this was your 2 pi over omega naught. So first time it completes one oscillation, that's your t naught. That is going to take more time. And in the extreme limit, when this wins over, it's going to be infinity. It doesn't come back at all. Right? The time period goes to infinity in the case of damping. So it doesn't come back at all. So that's should be what we look for. But for now, let's keep this. But we want to find A and B. So let's go back, and to find A and B, we also need velocity, right? So velocity is equal to, maybe I can erase this part, that is just for discussion. Oh, I think it's equal. So velocity of T. I have to take the derivative when I take the velocity, but notice derivative comes in 4 places now, not 2 places. 1, 2, 3, 4 places. So first one is I can have exponential fitting in. Could I do that this way? Maybe small change. You guys will have more trouble in incorporating this. A plus B. I just took the exponential out for once. So now I have only 3 derivatives to take. That's the advantage. So it is minus gamma times exponential of minus gamma t times A times cosine of omega naught squared minus gamma squared t plus B. And then I have to take the derivatives in both terms. In that case, it is simply whenever I take the derivative, omega squared surely comes out. So it is plus potential. Yeah. In here, it is A times sine, so it is minus A times sine. This is plus B times cosine. Right, that's fine. Velocity, basically taking the differentiation in the first step. If x was equal to x naught, I have X naught, I set time t equal to 0 everywhere. This is equal to 0, so it is A. And the next term is B, right? So A is basically X naught. That's right. This goes to 0, that goes to 1, and that is my A. That is the only thing that survives. Velocity at time t equal to 0 is V naught. That's equal to, again, time t is equal to 0, everything has to go away, so it is minus gamma. The sign goes away, so this is A survives. That's A. And the second term, it is the B that survives, so it's plus omega naught squared minus gamma squared. This goes away, and then it is B. A is X naught. So what we have is A is equal to X naught, and B is equal to A is equal to X naught, so it is V naught plus X naught times gamma over Okay. So let me do this and at least take a couple of limits. Change the cam. X as a function of time is equal to, go back in here, exponential minus t. It's not the sign. P is naught times gamma. I should point out that this might look more complicated than what you have seen earlier, primarily because I'm taking both the boundary conditions together. Like initial conditions, I'm taking both the position and velocity. So it is very general in that way. Whenever you want to say that initial velocity is 0, there is a lot of simplification. Or if you say initial position is 0, that's the best because then it gets really only one term. But if this is the case, let's have a scenario if whenever the gamma goes to 0, right? Or let's say what happens? So what happens when omega naught is exactly equal to gamma? So remember again, we were saying that if omega naught was very large compared to this is oscillatory. When gamma is very large compared to omega naught, that's damping term is. So somewhere in between is when they become equal. Right. So what happens in that case? That's called critical damping. But what happens to the solution? Like what happens especially in here?
Time is very small and so yeah, that's like that is square root omega.
So again, yeah, repeat that. That's correct. Yeah, I think what you think.
Yeah, the angle side is very small,
Uh-huh.
so we can write it as square root omega. Then both are cancel out.
Then you're assuming that P is very small. That's correct. So what you're trying to say is that when this is equal, that's almost 0, primarily 0, but don't think of it as a 0, but instead think of it as a limit. So in this case, apparently it is divergent, but it's not. Remember sine of theta over theta in the limit theta tends to 0 is equal to, right, that's equal to 1. All right. So we want to think about time being small compared to or the overall quantity fit. So theta has to be small, right? So the way you want to look at this is equal to exponential of minus gamma t x naught cosine of omega naught squared minus gamma squared times t plus I want to put in a time there, e naught plus x naught gamma. I multiply by a time and then I divide by time. It's fine. Omega naught squared minus gamma squared times t divided by now for whatever be the time, if this is really tiny, how much ever large this is, if I can make this small enough, and when I'm saying it is exactly equal to 0, then I'm really saying that for any time that quantity is 0, then in that limit, this is equal to 0. You want to argue that this is equal to 1, and that's your solution. Right? And in your quiz last time I had talked about what is the other independent solution. That's what your independent solution comes out to be. Remember, your omega naught is equal to gamma naught, right? That's equal to 0 q. So cosine of 0 is 1. So exponential minus gamma naught times x naught plus e naught plus gamma times t. So what will happen is that for some time this goes up. So there is this linear term also. So x is, if there was only exponential, this is how it looks like. T, that's your x. This is exponential of gamma t. Is it gamma or was it 2 gamma? No, minus gamma. Yeah, minus gamma, but not 2 gamma. That's exponential of gamma t. And now you have to multiply that with a linear term. Depends on what your initial conditions are and what your initial positions are. Whatever that is, it's possible that it might go like this. You'll eventually come back to that, but it can go up if you want. And it depends on the choice of your V naught. If all this was smaller, then it can also go down. So the initial velocity is the slope, right? That decides what exactly your curve will be for small time. For large time, all this is gone. So this is for large time. It is of course exponential of gamma. Eventually it will be. Eventually it will meet, but in the initial points, we don't know exactly what it will be. It depends on your initial conditions. So this is one of your homework problems where you want to analyze it. In the other extreme, I think I have already done where happens the spring. So you always want to see the extremes, what happens in this case, what happens in that case. It should go in that direction. And one of the cases when it is pure damping, that is straightforward. Cosine becomes cosine hyperbolic. The imaginary function associated with cosine and sine is cosine hyperbolic, and that we will see in a straightforward format. I expect you to do some plots also for this. Most of this analysis becomes much easy when you have plots associated with it. So I'll encourage you guys to use some plotting software, whichever is your favorite. That helps really. If not, that's up to you. I mean, it only helps you with the visualization, but otherwise it's not needed. I'll stop here, and this the exam is on Friday by default, unless Aryan.
You guys are okay. And Monday. Okay. So I'm traveling to Chicago over the weekend. it will be like no preparation over the weekend.
Okay, you guys think and tell me.
It's fine.
Also, it's going to be Friday. Okay. Okay. Okay, yeah, let's have it Friday. I think it's too late, so it's a talk maybe. Yeah. I think you're doing good in the exam, so concentrate more on the talk. I think that's my recommendation. Yeah, at least I typically say concentrate on other things before. Like most of you guys are doing okay, I think. Don't do too bad at the same time. Okay. Yeah, assessment is hard. Okay, Niranjan.
Thank you, Dr. Sajas. Then
Have you used Bessel functions in electromagnetism yet? In your electromagnetism course? Bessel functions, legendary polynomials? Yes, legendary polynomials, okay. Spherical harmonics? Spherical harmonics? So no quizzes and the thing, so yeah.
So this is the over.
Oh,
So
there's
you
a,
are being
oh,
submitted.
yeah, yes, thank you. Yeah. Still bit, I think,
Yeah, I play.
I'll accept it, yeah.
This weekend, that's like the motorcycle training course. And
Uh-huh.
it was 20 hours. And
20 hours? So you have to do, how do you do 20 hours at a stretch?
we did 8 to 6 Saturday and Sunday, and then on Friday we were there from 6 to 9:30.
So is it necessary that you have to do this at a stretch?
Yeah, they make you.
So they make it tired and you still have to be good. Is that the point?
I passed. So
Okay, wow.
yeah,
So you're on the motorcycle for 20 hours? In
for
that,
about half the time we are.
Half the
Another
time.
half the time's in a classroom, just cramming. It was awful.
wow, yeah, that seems. So that is the purpose though, that you want to tire. But in the normal driving, they don't do that.
No,
So they should do more that more on the normal driving so that people fail and but then people really need to drive, I guess, for getting the commute done. Okay. Yeah, relax and get it done, but let's say in 2 days or so.
Yeah.
Yeah. Catch up. Or how about this? By this exam, catch up on everything. No deadline on Tuesday or Wednesday. But by the time of
I'll try to get
exam,
to before.
yeah, exactly. Yeah.
Okay.
Get it done because
Uh,
it will never get it. If I keep relaxing, then
yeah,
it'll-
I know how.
yeah, okay.